So let's now take a look at the second law of thermodynamics. For the second law of thermodynamics, we have what can be counted as the two statements of the second law of thermodynamics. We have what counts as the engine statement and the other one as the refrigerator statement. Kelvin Planck statement or the engine statement of the second law of thermodynamics tells us that basically tells us that no heat engine has a 100% thermal efficiency. Not all of the input heat QH may be converted into mechanical work. There's always that wasted energy QC that needs to be discarded into the cold reservoir. It is impossible for any system to undergo a process in which it absorbs heat from a reservoir at a single temperature and converts heat completely into mechanical energy. There's always that wasted energy QC that needs to be discarded. On the other hand, you have the refrigerator statement or the Clausius statement. It tells us that it is impossible for any process to have as its sole result the transfer of heat from a cooler to a hotter body, meaning it's impossible to simply have heat from the cold reservoir go directly to the hot reservoir. We also we always need to have input work or QC for heat to be taken from heat QC to be taken from the cold reservoir. On its own, heat will not flow from cold to hot reservoir. The second law of thermodynamics is basically an expression of the inherent one-way aspect of irreversible processes. One example of an irreversible process is the baking of bread. That is to say, you use heat to turn dough into bread. This process happens only in one direction. It's an irreversible process. Bread will not on its own change back into dough and give off heat, although that process does not necessarily violate the energy conservation principle. Bread will not change back into dough, giving off heat as a result, because the baking of bread is an irreversible process. One quantity or property that determines the one-way direction of irreversible processes is entropy S. For a closed system, the entropy is always increasing for irreversible processes and constant for reversible processes. The baking of bread is an irreversible process because when you look at the quantity entropy for the breaking of bread, the entropy is always increasing, which means the baking of the bread is an irreversible process. If the entropy was constant, then that would mean that the baking of the bread is a reversible process and the bread can turn back into dough. We have the equation form of the second law of thermodynamics in terms of entropy. The change in entropy is always greater than or equal to zero, meaning either the entropy is constant, delta S is constant, or the entropy is increasing, delta S is greater than zero. Entropy is will never be decreasing. It's either increasing or constant. Either the process is irreversible or the process is reversible. Reversible, delta S is 0. Increasing delta S, irreversible process, the delta S is greater than 0. Entropy may be seen as a measure of the amount of thermal energy that is unavailable to do work, like in the case of heat energy, of heat engine rather. You'll recall that in a heat engine, you take heat from the hot reservoir to perform work W. So basically, you convert QH to W, but not all of QH is converted into W. The excess heat QC is discarded by the heat engine. Not all of the thermal energy is available to perform work. In this case, entropy is defined as delta S. The change in entropy is equal to S final minus S initial is equal to integral of dq over T. dq over temperature as you integrate from initial state to final state. For relatively small temperature changes, entropy change may be approximated. This integral may be approximated as delta S is equal to Q over T average, where T average is the average temperature of the system in Kelvin. Let's take a look at one application of this equation, the Carnot engine. The Carnot engine or the Carnot engine. We can study real engines by looking at the behavior of ideal engines. One ideal engine is the Carnot engine. Carnot engine is still a heat engine, so it's a cyclic. It involves a cyclic process. So delta U is 0, which means W is equal to Q. And Q is just equal to QH plus QC, or absolute value of QH minus absolute value of QC. Delta S is Q over T for small temperature changes. So much so that we can say temperature is or can be considered as constant. So Q over T, meaning if you have QH, then you have delta SH. And if you have QC, you have delta SC. And delta S is equal to delta SH plus delta SC, the total change in the entropy of the system. Now, delta S is equal to or greater than 0. Heat engine involves a cyclic process. So basically, it involves a reversible process. So delta S is equal to 0. Delta SH is QH over TH, whereas delta SC is QC over TC. And this is equal to 0, which means we can rearrange the equation to be QC over QH is equal to TC over TH. Putting this relationship into the equation for the heat engine thermal efficiency, E is equal to 1 minus absolute value of QC over absolute value of QH. We get 1 minus TC over TH, and this is equal to EC, the engine efficiency of the Carnot engine. So the Carnot engine efficiency. engine efficiency for an ideal heat engine. Since this is efficiency for an ideal heat engine, no real engine can have a thermal efficiency greater than EC. Seeing as again, EC pertains to an ideal engine. And that's it for now. In the next video, we'll talk about the examples part of our discussion on the second law of thermodynamics. So thank you for watching.